to talk about the challenges to the existing distribution system and the proposed solutions. The existing power system was designed to work with controllable generation connected to a bidirectional transmission system to meet the real-time load demand. The existing grid protection and control devices were all based on these existing characteristics. The existing distribution system is supplied by the transmission system and designed for low-cost distribution of electric power over a wide geographic area in a radial or tree or unidirectional fashion. Typically, the distribution feeders are sized with progressively smaller conductors to serve expected load with minimal redundancy. All of the distribution control and protective devices were designed for radial flow, single path from central locations. Here are some power system fundamentals. Any power grid, including microgrids, needs to have a dynamic power balance between generation and load for stable operation. All electrical equipment need to be operated within their respective ratings. The distribution system is typically required to regulate service voltage to plus minus 5% of nominal. This voltage regulation is normally done by radial voltage regulators on the distribution system and not on the transmission. Protective devices on the radial distribution system were mostly time over current devices, and they are coordinated in the radial direction. They were not designed to work in the reverse direction. Here is a representation of the traditional electric power system. And here we show the transition from the existing grid to the new grid with a lot more generation resources all over the place. It's a lot more complicated. Here I'm showing the service voltages and the voltage ranges that's allowed. And also show in the bottom graph the potential voltage with or without DERs. The main distribution challenge is the proliferation of intermittent renewables that do not meet the local load demands and cause voltage and protection problems. Currently, the DERs are allowed to operate at full available output to maximize renewable energy. They do not follow local load and often exceed local load and cause significant reverse flow on the distribution main line. The reverse flow may cause high voltage violations on the distribution system. At low penetration levels, if the DER outputs are consumed by the local loads without reverse flow, they usually do not cause any problems. At higher DER penetration levels, the DERs may exceed local load and cause reverse flow. The existing distribution protection and control devices were designed for radial flow and not reverse flow. Hence, they may not operate properly under reverse flow conditions and cause various operating problems. So here's a proposed methodology to address these challenges and still enable the adoption. The key is to couple these resources with storage to convert the intermittent resources into controllable resources that can actually support a grid load. For all new installations, couple these units with sufficient storage and set up the local system for non-export. Excess PV energy during the day should be stored for nighttime use and not exported or curtailed. When the DER system does not export, the existing distribution system will be operating normally and distribution upgrades may be minimized. Also, the fault contribution from the DER inverter will also be minimized since the inverter is sized to the load and not oversized. The PV plus storage can be operated in microgrid mode and used to serve local load during outages. The unit may also be set up to charge EV if available during the day, but they may need to be sized appropriately. The customer may still use the grid power during the wintertime and storm season when the PV output is lower or not available. For higher renewable penetration levels, for the grid side projects, couple these units with adequate energy storage to enable intermittent renewable energy resource facility to follow local load and or provide necessary dynamic, real, and reactive power support under the operator direction. Require communication control capabilities between the larger units and the grid control centers. Upgrade the existing grid operating system to provide real-time renewable visibility and enable the grid operator to actually control these units for grid support. Conclusions. Any engineered system, including the power system, needs to operate within the design parameters until the system has been redesigned and or rebuilt. New concepts may need to be piloted and be proven cost-effective for the intended mode of operation before widespread adoption. Until the new concepts are proven cost-effective and the distribution system upgraded, the existing distribution system should be maintained to minimize cost or repair impacts. Thank you.